Hi everyone, it's Mr. Edie back with yet another video. So today, guys, we're going to talk about energy of phase changes. Okay, so as we discussed in 6.4, we can calculate the heat that is required to increase or decrease the temperature of a particular substance using Q equals MC delta T, right? And this is illustrated on the red points of this curve. So when the temperature is rising for this particular substance, we use Q equals MC delta T to see how much heat was required to do so for that given temperature change, right? Now, today, guys, we'll be able to calculate the energy at the plateaus where the phase change is actually occurring. So to do so, guys, we can find the heat of fusion, which is it's melting. All right, so this is when the substance would undergo the melting phase change using Q equals the number of moles times the enthalpy of fusion, that's delta H, or the heat of fusion is equal to the mass times the enthalpy of fusion. So the question is well, Mr. Edie, when to use moles, when to use mass? And the short answer is, guys, depending on what they're giving you in the problem. So if they give you mass, use Q equals M times delta H. If they give you moles, use moles. Okay. And of course, they could be asking you to find this. No, use the units that they're given. Just keep it simple. Okay. The heat of vaporization, which is its boiling point, okay, we're going to use Q equals the number of moles times the enthalpy of vaporization, or the mass times the enthalpy of vaporization. So two very simple equations at these plateau points, okay? So just as a quick reminder, Q is your heat, moles is N, mass would be M, delta H, fusion or vaporization, is the enthalpy of fusion or vaporization. Now, again, guys, you're going to pick the equation you're going to use. So if they're giving you moles, I'd use the top one. If they give you mass, use the bottom one. Very simple. Okay. Now, why do we need two different calculations in the first place? Well, as we just got done saying, right, the rising or falling parts of the heating curve are corresponding to the system simply increasing in temperature. Okay, so that's very simple. So that's why we use Q equals MC delta T. Now, at the plateaus, that's indicating the actual phase change. Okay, so notice that the energy is increasing, right? We're still absorbing heating to our system, but the temperature has not moved. Well, that's because, folks, this is indicating a change in potential energy because intermolecular forces are being broken. From go to the solid state to the liquid state, I have to break some intermolecular forces. And then again, from the liquid state to the gaseous state, I have to break intermolecular forces again. So note it, the energy difference at the boiling point versus the melting point, right? We just went from a solid to a liquid. That's why it didn't require so much energy, because I didn't have to break many intermolecular forces there, right? Liquids still have their intermolecular forces. They're just a bit weaker so that the molecules can flow on top of each other. But once we get from the liquid state to the gaseous state, I have to push these molecules or atoms so far apart, right? And that means I have to essentially break their intermolecular forces completely, right? So that's why I need so much more energy to do so. So that's why the energy difference here is pretty radical, right? It's a pretty high difference in energy from going at the boiling point versus the melting point. All right, so keep that in mind. As a reminder, guys, going from the solid state to the liquid state, from the liquid state to the gaseous state, that is an endothermic process. Okay, where an exothermic process would be going from the gaseous state back to the liquid, because you have to take heat out of the system, and then again from the liquid to the solid, you have to take heat out again in order to freeze something. So here's a heating curve illustrating when the process is being endothermic versus exothermic, and here's a really nice simple diagram of having all the states of matter illustrated. Okay, well, here's the energy of the system. What does it look like? Okay, well, at the solid state, at melting or fusion, I have to put energy in. That's endothermic. To go from the liquid to the gas, that's vaporization. I have to put energy into the system. So again, endothermic. But if I go from the gas directly to the solid state, that's deposition. That's an exothermic process. The energy has to be released. So, uh, you know, These diagrams are for you. So I would draw whichever one makes more sense for you in your notes. That way you at least have it there. Okay, so calculating the heat needed at phase change. So to calculate the heat needed to perform phase changes, we use the enthalpy for that phase change and multiply it by the amount of material. That was the delta, or I'm sorry, that was Q equals the number of moles times the delta or the enthalpy of fusion, or Q equals the number of moles times the enthalpy of vaporization. We talked about those two equations. That was at the very first slide in this presentation. Enthalpies of fusion and vaporization, guys, are different for each substance, as you can take a look in this table 7.2 next to the bullets. And they're typically given to you. Like, it's often, unless they're going to ask you to solve for this number, they're typically given. So note that these are all in kilojoules per moles. So if I was using these formulas, I'd probably be converting my material into moles, just to bring it to you like that. All right, so let's dive into an example problem. So it says, given the heating curve for mercury, calculate the heat to freeze 100 grams of mercury HD at its melting point. Okay, well, guys, keep in mind, we need we're trying to find Q, so Q equals, and take a look here, guys. They gave us the heat of fusion in kilojoules per mole. Okay, so since they gave us kilojoules per mole, I'm going to use the number of moles times the delta H of fusion. Okay, so keep that in mind. Well, since I have since the problem, it's originally gave me grams, right? Since I was originally given 100 grams of mercury, I first got to convert that into moles. So 100 grams of mercury. Okay, so grams of mercury on the bottom, moles of mercury on top. Okay, we know it's going to be 1 mole times. All right, so it's 100 grams of mercury times 1 mole divided by 200.59 grams. So when we do this calculation, we get 0.4985 moles of mercury. Okay. From here, we're going to just plug this into our equation. So Q equals 0.4985 moles of mercury times our melting point, our heat of fusion, which is delta H, which is right here, guys, 2.30 kilojoules per mole. Our moles are going to cancel out, so we can cross those out, and we're given our answer, which is the heat of this, the heat that is going to be released is, okay, so our heat release will be 1.147 kilojoules, okay? So you could say is released like I did here, or because we know this isn't going to be an exothermic process, you could also put the negative 1.147 kilojoules, indicating that you know it's an exothermic process. Personally, guys, I would have just said the heat released is 1.147 kilojoules. Okay. And with that being said, guys, let's jump into number 2. Okay. So number 2 says we want to calculate the heat at each segment of the curve for 1 mole of water to completely transition from ice, then to its liquid state, then to finally steam. So guys, what I'm essentially asking you to do is I want you to calculate the energy required to increase ice to go to its melting point. So that would be segment 1. Segment 2, ice to melt from a solid to a liquid. So that's segment 2. Segment 3, raising our temperature up to the boiling point. And then finally, segment 4 is our phase change at this boiling point. And then let's say, well, that's the end, right? Because at this point, our mole of water will have completely vaporized. So we'll stop at segment 4. All right, so I'll walk you through segments 1 and 2, and then I'm going to have you do segment 3 and 4 on your own, okay? So Let's dive right into this. So we have 1 mole of water. So something that's going to be useful for us is to remember that 1 mole of water is equal to 18.015 grams of water. Okay, because we do have to use different equations throughout this process. Okay, and then it's asking us to calculate segment 1, right? So here is segment 1. I'll redraw it in blue for us. So that's segment 1. Okay. So let's do this. So at segment 1, since the temperature is just increasing, we're going to use Q equals M times the specific heat of ice times delta T. Okay, so now we're just going to plug in our numbers. So we have 1 mole of water, so that's pretty easy. We're going to do 18.015 grams of H2O times the specific heat of water. That was given to us. It's over here, guys. It's 2.05 joules per gram degree Celsius times the change in temperature. Guys, we'll just say for argument's sake that the ice is at negative 10 degrees Celsius. So we're going to do 0 degrees Celsius is our final temperature minus negative 10 degrees Celsius. I know that's not the scale, but for argument's sake, we'll say it is. And now we're going to plug and chug this into our calculator. I'll be back in one moment. All right, and I get Q equal to 369. We'll say 369 joules is the amount of energy required to move the energy from negative 10 degrees Celsius up to 0. We could also say, or 0.369 kilojoules. We're probably going to, we don't have to, guys, but if you wanted to, we could convert this into kilojoules. The reason why we don't have to is because they gave us our enthalpies of fusion and vaporization in joules per gram. So again, guys, it's ultimately up to us on what we want to do there, but joules here would have been sufficient. But if they gave us our enthalpies of fusion and vaporization in kilojoules per gram, we probably would have wanted to convert it so it's easier to compare numbers here, but we didn't have to in this case. Let's do the plateau point now, which is segment 2. So here's segment 2, guys. We're going to now switch our formula to Q equals, we definitely need the delta H of fusion, but note that they gave us joules per gram. So instead of using moles here, guys, I'm going to use M. So Q equals M times the delta H of fusion. Okay, so now I'm going to plug in what we've got. So we've got 18.015 grams of water. Again, that's just simply equal to 1 mole of water. I'm not making that number up. Okay, and then our heat of fusion is 334 joules per gram. So the heat required to occur at this phase change, so from our ice melting to the liquid state, is 6,020 joules. Okay, so that's the heat required in order to have our phase change occur here. From the solid state to the liquid state, it takes 6,020 joules in order to break those intermolecular forces. So guys, what I want you to do now is pause the video, and I want you guys to try and solve the heat required from at segment 3. So let's assume that's at 0 degrees Celsius to 100 degrees Celsius. The heat required to undergo this temperature change. Okay. And then the second thing I want you to do is to calculate the energy required to actually go from the liquid state to the gaseous state, or to go from the liquid to steam. Okay. So pause the video and try to do those calculations on your own. Okay, guys, and I hope you were able to get that the energy required to change the temperature from 0 degrees Celsius to 100 degrees Celsius was 7,530 joules. Meanwhile, the energy required to go from liquid water to steam was 40,700 joules. And guys, keep in mind, that makes sense because you had to break the intermolecular forces between the water molecules in order to put them into the gaseous state. And with that being said, guys, that's the end of today's video. If you have any questions, please feel free to shoot me an email.